All right, welcome everyone to Chapter 6, the integral. We're starting here a little bit strange in section number 3, the definite integral. And so let me tell you a little bit, right, about the definite integral. And the claim is, well, up until this point, you may feel like, right, a one-trick pony. We've been spending a lot of time with derivatives. I mean, I know at the very beginning of the course, we did a little bit of an algebraic review, and then we talked about it with limits, in order to talk about derivatives, and we talked about average rate of change in order to talk about instantaneous rate of change, aka another phrase for derivatives. We've talked about applications of derivatives and tips and tricks in order to take derivatives faster, like the product rule, the chain rule, things like this. And so we've just been doing derivatives, and now finally we're going to talk about maybe the second big idea here in calculus, and this is going to be called integrals. And so let me tell you a little bit about these things. Again, in this section, we're going to be talking about this thing called the definite integral. And the definite integral, well, you need a specific function, f of x, and you need a specific interval. So in this case, I'm going to do the interval from a to b. And this has a little bit of a strange notation, which we'll go over later, but it looks like this. It's a big old S, and then there's a subscript a, superscript b, so this is specifying the interval. And then you put the function in here, and then sometimes, well, I guess this variable changes, right? So it's not always x's. So you specify what you're integrating with respect to, a little bit strangely. So this is a little dx here. Again, we'll go into why this is here a little bit later, but for right now, just take its b notation. So again, this is the interval ab. Here is our function, and let's get to it. So, right, so what is this thing? Well, the claim is it is the net area between f of x and the x-axis on our specified interval, on the interval from a to b. Sometimes we say this is area under the curve, but if you think about it, area under a curve would go on forever. So, right, it wouldn't be really finite area or anything like this. It would go on forever. So really, when you see, area under the curve, you have to think it's the area between f of x and the x-axis. Okay. So that being said, the second big idea in calculus is going to be area between curves. So let's get started with a few practice problems here using this notation and whatnot. So the first one here, evaluate out the definite integral of 4 over the interval from 1 to 3. Right, so our function is the constant function 4, our interval is 1 to 3, right, and I've included here the first couple problems, some alternate phrasing that you may see pop up, right? You may see determine the area under f of x equals 4 on the interval from 1 to 3. Okay, so I want area under, well, let's actually visualize this thing, right? Let me actually draw this out. So here is my nice coordinate axes. And I'm interested on the interval from 1 to 3. So here's 1, 2, 3. I have the function, the constant function 4, right? 1, 2, 3, 4. And it's a constant function, so it's just a nice horizontal line. No matter what x is, it's always spitting out 4. And I would like the area between this function and the x-axis. So I'm going to draw kind of some dotted lines down to the x-axis. Only on the interval from 1 to 3, right? The function exists, everywhere, right? You can go down to 0 or down to negative 30 or wherever, right? And you can go up to positive 50 and all these sorts of things, right? It goes on forever in both directions, but we only really care right now the area under the function on this interval. Only between 1 and 3 are we caring about. So I want to figure out the area right here. And if you stare at this, right, it looks familiar. It looks like a rectangle, right? And so I can figure out the area of this by remembering what the area formula for a rectangle is. Okay, so in order to apply the area formula for a rectangle, well, I need to know, right, a length and a width, or a base and a height, or, right, there's lots of different phrases that you can use. So in this case, my base has length 2, and my height has length 4, right? So the area is going to be 2 times 4, which is 8. So this definite integral thing from 1 to 3 of our function 4 dx is equal to 2 times 4, which is 8. And that right there is my final answer. All right. one problem down. Let's try a little bit more of a difficult one here. This time I do not have a constant function. I have the function x plus 5, so it changes depending on which x value you plug in. And I'm interested on the interval from -1 to 4. So again, let me go ahead and draw some coordinate axes, because I really want to visualize this. It's very geometric. Okay, and I want from -1 to 4. 1, 2, 3, 4. 1, 2, 3, 4. And let's see, I'm going to want to go ahead and sketch this thing. Let me put some tick marks along my y-axis. I need a decent number of them. We'll start with that. Okay, so again, I'm trying to sketch this function x plus 5. So if I was to go ahead and plug in 0 for x, for instance, I would get out 5. 1, 2, 3, 4, 5. If I was to plug in -1 for x, I would get out 4. If I was to plug in 1 for x, right, I would get out 6. Yeah, 1 plus 5, 6. If I was to plug in 2, I would get out 7. If I was to plug in 3, I would get out 8. And if I was to plug in 4, I would get out 9. Right? Now, really, you only need 2 points in order to sketch a line, right? Because, well, it's a straight line. So something like this. So there is my function, x plus 5. Now let me go ahead and kind of highlight some important ones, right? This was 9, kind of where we stopped. We cross here at 5, and we get down, maybe our lowest point here is 4. Those are some important y values. Okay, just as before, I want the area trapped between this curve and the x-axis. So if we'd like to, you can say area under this curve, on the interval from -1 to 4. So let me go ahead and highlight this again. So this is the area that I'm trying to find. And if you stare at this for long enough, you may recognize that this is actually a trapezoid. And so if you remember the area formula for a trapezoid, you could use that, right? And you could figure out the area of this thing. I'm going to pretend, though, that I don't remember the area formula of the trapezoid. And instead, I can realize that I can break this up into a couple pieces, right? All trapezoids, you can kind of do this. You can break them up. And if I break it up into 2 pieces in this case, right, you can see I have a nice triangle on top, and I have a nice rectangle on bottom. And this, I certainly remember the area equations for. Okay, so let's go ahead and write down our definite integral from -1 to 4 of x plus 5 dx is equal to. All right, and so I have the area of my rectangle. So my rectangle has height 4, and its base is length 1, 2, 3, 4, 5. So height 4, base 5, so this is going to be 4 times 5. I know that's 20, I'll get to that in a second. And then I need to add on the area of my triangle. So let's see. This has height 1, 2, 3, 4, 5. Right? So this height right here is 5. And its base is the same as the base of the rectangle, so this is 5. So the area formula of a triangle is 1/2 base times height. So I get 20 plus 25 halves, right? And if you go ahead and you plug this into your calculator, you'll get out 32.5, right? So the claim is the area under this curve, x plus 5, on the interval from -1 to 4 is 32.5. All right, we have 2 examples down. We have a constant function, we have a linear function. The claim is these 2 really undersell, right? So I have the remark down here. These 2 really undersell the difficulty level of area under a curve, right? Because these were awfully geometric. However, not every function is so geometric, right? And so therefore they can be much more difficult. And so let me kind of emphasize this by setting up the area under the curve, right? This definite integral from 0 to 2 of x squared. Okay? So our function here again is the x squared function. And I'm just interested on the interval from 0 to 2. So, okay, if I was to plug in 0 everywhere I see an x, I would get out 0. If I was to plug in a 1, 1 squared is 1. If I was to plug in a 2, 2 squared is 4. And I could go on. And of course, this function exists kind of everywhere, but I only care right now about the interval from 0 to 2. And so if I was to try to sketch this thing, right, it looks like a parabola. It looks awfully curvy. We know that these quadratics are, right? So something like this. I probably made mine a little too curvy, right? And we only care about the area between 0 and 2. And my highlighter's too thick, but okay. Something like this. We're trying to figure out this area. And so does this look like any geometric shape? And the claim is no. It actually looks, well, kind of, it looks like a triangle, right? But triangles have straight lines. So this isn't quite a triangle, it's something else. Again, it's kind of close to a triangle, but not quite. So I don't know any geometric formulas for area under a parabola like this. So as of right now, the answer is no. We don't know any geometric formula. Geometric formula for this kind of area. So as of right now, we're stuck. And the claim is later on we will come back to this and we'll be able to solve problems like this. But for right now, we're going to go ahead and learn how to approximate area under more difficult curves, kind of like this one and even beyond this one, thanks to an idea courtesy of this guy, Bernhard Riemann. So this is a famous German mathematician. I have his Wikipedia page right here. In fact, I have it pulled up just so you can kind of see what he looks like. He was alive in the 1800s, had a very famous doctoral advisor, Carl Gauss, and had his hands in a lot of different fields of mathematics. And in fact, I have a little bit of a bonus exercise for you. There is a very famous problem in mathematics that actually, as of right now, it's called this, you can actually win $1 million if you can solve it. It's called a millennium problem, right? And this was originally proposed by Bernhard Riemann, and it's known as the Riemann hypothesis, right? It got named after him. And so the claim is I have this nice video that you can start to understand about it. It is a very difficult problem. It's been described as one of the most difficult ways to win $1 million. So again, it's a very difficult problem, but like I said, he had his hands in a lot of different fields of mathematics, and he came up with this very difficult problem that we still don't know if it's true or not, right? We think it's probably true. We haven't been able to come up with any counterexamples, but he asked a really good question, and and this was in the 1800s, like 1860 or so, and we still have no idea. Again, like I said, we think it's true, but we haven't been able to prove it, and we haven't been able to show that it's false. So, all right, that's kind of on the side. For right now, though, his idea in order to approximate area under curves is called Riemann sums, again named after him. And we need nice continuous functions. And in that case, we can define something called the left Riemann sum, which is sometimes denoted LHS. Sometimes it's actually called left-hand sum, or left Riemann sum. These are kind of equivalent. And the right Riemann sum, or right-hand sum, right Riemann sum, right-hand sum, so RHS, with n equal subdivisions of f over a specified interval, just as before, a to b. Remember, we're using these things to approximate area under a curve, can be defined as, all right, so LHS is equal to, and the notation gets a little bit crazy. I'll explain here in a second. So here we go. This is f of x sub 0 times delta x plus f of x sub 1 times delta x plus, and this goes on however many subdivisions you want minus 1. So if you want n subdivisions, we're going to do x sub n minus 1 times delta x. And that's how we define the left-hand sum. The right-hand sum is very similar, But instead, we start at f of x sub 1 times delta x plus f of x sub 2 times delta x all the way up to the nth, f of x sub n times delta x. And this specifies that actually x sub 0 is equal to a, that x sub n, this last endpoint, is equal to b, and this delta x right here is defined as b minus a over n. Whew. So the claim is here, right, that we actually do need this notation and this idea for our next video. But as of right now, this is crazy complicated, right? This is just mumbo jumbo, and the claim is that it's actually a fairly simple idea. And so let me actually show you this in action, and then I'll show you what the simple idea is. So we're going to go ahead and determine the left-hand sum, or the left Riemann sum, of f of x equals x squared on the interval from 0 to 2 with two equal subdivisions, right? And that means that n is equal to 2, right? N was supposed to be this number of subdivisions. Okay, so let me go ahead and start sketching things out, right? I want from 0 to 2. I'm just going to do kind of the one-dimensional number line here. And so our a here is 0. So this is a, and this is b, right, from our previous notation. So 0 is the same thing as a. 2 is the same thing as b. And we see that x sub 0, this crazy thing, right, is supposed to be x sub 0, right? So a is x sub 0. And then b is supposed to be x sub n, right? So in this case, we want 2 subdivision, n equals 2, so this is x sub 2. And if we want equal subdivisions, and we want 2 of them, right, I want to split this interval into 2 equal pieces. The claim is, well, I should chop it in half. And so this value 1 right here is x sub 1. So we have x sub 0, x sub 1, x sub 2, right? These are all different x values. Okay, and so according to this, if you want the left-hand sum, you would want LHS is equal to f of x sub 0 times delta x plus f of x sub 1 times delta x, and then you stop, right? Because 2 is our n in this case. 2 minus 1 is 1. So you stop and you get to x sub 1. Okay, what is our delta x? Well, up here, delta x is supposed to be b minus a over n. So our b value, again, is 2. Found it right here. Our a value, 0. And our n value, 2. So delta x is supposed to be 1. So again, let's go ahead and plug this in. F of x sub 0. Well, x sub 0 is the same thing as a, which we learned is 0. Delta x, that's going to be 1. That's what we found up here. In fact, let me label this delta x. F of x sub 1. X sub 1, as we learned here, right, this is halfway point. This is supposed to be 1. Times delta x. Delta x also happens to be 1. How do I get f of 0? Well, I just plug it into my function, right? So if I plug in 0 into my function, I would get out 0. So 0 times 1 plus f of 1. So if I was to plug in 1 into my function, I would get 1 squared, which is also 1. And this simplifies down to 0 plus 1 equals 1. So this is how I read and use this notation. But the claim is, again, that this is actually a relatively simple idea. And so I want to share with you now what that simple idea is. So again, let me go back up to this picture. We already have the x squared function here. And if I want to estimate, again, the area on this interval from 0 to 2 with 2 equal subdivisions, as before, I'm going to split this up into kind of 2 sub-intervals almost, right? So from 0 to 1 and from 1 to 2. And in order to approximate the area under this curve, I'm going to use rectangles, right? So we saw that we were multiplying actually what was a length of a base and a height, right? The function's value, oh no, the function's value gives out heights, and this delta x Well, that happens to be the exact widths of those two subintervals. Let me show you again. So up here, if you break it up into two subintervals, right, each one has width 1. So this is a length, or a width, I guess maybe, or a base, if you'd like to call it that, times a height, right? The function's value gives out heights. And so on this first subinterval, right, if you use the height over here on the left-hand sum, or left Riemann sum, right, you would have the height is 0 times the width is 1. So on this little subinterval, you would say, okay, I'm going to approximate this area as 0. On the next subinterval, again, the width is 1, and if I use the left-hand sum, or the left Riemann sum, right, so on the left-hand side of this subinterval, you would say that its height is 1. So you have 1. And so you have a 1 by 1 rectangle, and so you can approximate the area under this function as, well, the area of this rectangle, 0, plus the area of this rectangle, 1, and so you get out 1. Now, as far as you can see, this is a pretty cruddy approximation, and we'll actually talk about ways to make this better. But again, the idea is just simply rectangles, right? We're going to use rectangles along with the function's height values, right, in order to approximate area under a curve. So, let me actually have included some space for us to write some of this important information down. So again, we can see that Riemann sums are just using rectangles to approximate area under a curve, where n is the number of rectangles and delta x is the width of each rectangle. Okay, let's try this again with another function. This is a pretty complicated function, very hard. There's really no geometry under this curve that we know an area formula for. So I'd like to go ahead and calculate out the right Riemann sum of f of x equals 2x over 1 plus x squared on the interval from 0 to 1 using n equals 5. Okay, so I'm going to think again. I have the interval from 0 to 1. And I would like to break this up into 5 even pieces. And the question is, how big should each piece be, right? And so if you'd like to, if you remember the delta x formula, right, you can use 1 minus 0, that's b minus a, divided by n, 5, and you get 1/5, which is the same thing as 0.2. So if I break this up into sections of 0.2, the claim is I'll have 5 of them. So if I go 0 to 0.2, and then I go to 0.4, and then I go to 0.6, and then I go to 0.8, right? The claim is that I have 1, 2, 3, 4, 5 equally spaced pieces, right? And those will become our rectangles. As of right now, they each have a width of 0.2, 0.2, 0.2, 0.2, 0.2. Okay, so we have the widths of our rectangles. Now we need to figure out the heights of our rectangles. And in order to do that, we're going to plug these things into our function. So actually, at this point, let me go ahead and make a table. So I have the value 0, 0.2, 0.4, 0.6, 0.8, and 1. These are all x values. And I'd like to plug them into my function and get out y values. These will be heights of rectangles. Okay, so in order to do this, in order to plug in many things into our function, it's a good idea to use our calculator. So let me go ahead and pull out our calculator. And turn it on, y equals, and oh, looky here, right? I already plotted this function for us, 2x divided by 1 plus x squared. And I would like it at specific values. Notice the jumps are 0.2, so I'd like to go into my table set, second window, and notice I'm starting at 0, and I'm doing jumps of 0.2. so that way I can actually see all of these values. So now let me go into the table here really quick. So the table. At 0, the function spits out 0. So we can check this one pretty easily, right? If I plugged in 0 everywhere I saw an x, I would get 2 times 0, 0, divided by 1 plus 0. So 0 divided by 1, okay, that would be 0. If I plugged in 0.2, I would get out this 0.384 and change. If I plugged in 0.4, 0.6, 0.8, 1, right, I get all these different heights. So now let me go ahead and write these down on my paper really quick. So 0, I get out 0. When I plugged in 0.2, it was 0.38. I'll round up to 5. Here we have 0.690. Here we have 0.882, 0.976, and then here we have 1. So again, I want you to think that we have these 5 different intervals here. I have from 0 to 0.2, from 0.2 to 0.4, from 0.4 to 0.6, from 0.6 to 0.8, and from 0.8 to 1. So these 5 different intervals, and we want to use the right Riemann sum. So that means on the first interval here, when I have a choice between kind of this left endpoint and this right endpoint, I'm going to go with the right one. And then again, on the second interval, I have a choice between the left and the right. I'm going to go with the right one. Here on the third interval, I have a choice between the left and the right. I'm going to go with the right one. On the fourth one, a choice between the left and the right. I'll go with the right one. And then on the fifth, I have a choice between the left and the right, and I'm going to go with the right one. So basically, you can see I have all of the values here, except for I missed this one here on the left, which kind of makes sense because I'm using a right Riemann sum. So these are going to be the heights of my rectangles. So now let's go ahead and write this out. Again, all of the widths are going to be 0.2. So I have 0.2 times the right one. So this is going to be 0.385 plus 0.2 times 0.690 plus 0.2 times 0.882 plus 0.2 times 0.976 plus 0.2 times 1. All right, let me go ahead and plug this into my calculator here and get our approximation. So again, 0.2 times 0.385 plus 0.2 times 0.69 plus 0.2 times 0.882 plus 0.2 times 0.976 plus 0.2 times 1. Whew. 0.7866. And this would be my value. But again, right, this has some geometry behind it. It means something. So I actually want to show you again the graph of this function, what exactly we found. And so let me go ahead and pull up our nifty tool Desmos over here. So here is the Desmos. And you can see that I have our function, 2x over x squared plus 1. You can see that my left endpoint is 0, so my a value is 0. My b value is 1. And you can see that I'm using, the number of intervals here is 5. That's the number of rectangles, right? And so as of right now, you can see that, so I have this little switch down here. So c equals 0 is for the left-hand sum, or the left Riemann sum. And when I switch it and make it c equals 1, this is for the right-hand sum, or the right Riemann sum. And so if I switch it like this, you can see that, again, these areas of rectangles approximate the area under the curve here. They get kind of close. Again, it's hard to actually figure out exactly what it is. But let's see if you can, at this height right here, you can see 0.385, right? So that was the height, again, and the width of this rectangle was 0.2. If I go over here, we can see that the height here was 0.69. Here, the height is 0.882. Here, the height is 0.976, and here the height is 1. And that's exactly the numbers that we wrote down, right? Notice that we don't have the value 0 here, right? It starts at 0.385 because we're using all right-hand sums. On the other hand, if you were to switch this and use left-hand sums, right, our first value actually would be the 0. So we would have at 0, that's height 0, and then all the way up to, we would include the, oh, it's hard to get there, we would get the 0.976, but we would not get the y value 1 at all. And now, like I said, eventually we'll see how we can better approximate the area under the curve. And actually, while I'm right here, I'll show you. The claim is going to be if we use more rectangles, we will get a better approximation. So let me show you here. If I increase the number of rectangles, look at how good the approximation comes. And in fact, so here at 48 rectangles or so, it's so very close. I mean, they are actually all still rectangles. If I zoom in, you'll see they're still rectangles. But the claim is the area is being very well approximated by these rectangles. And here's at 100. So very many rectangles actually does a really good job of approximating this area. Here, let me do maybe the saddest case. If you just have one rectangle. Well, if you have the one rectangle and use the left-hand sum, well, the left is 0. If you do a right-hand sum, right, so here the right-hand point is 1. So again, this is kind of the saddest case. If I can pump this up maybe to just 2, this is what it looks like. Right-hand sums, left-hand sums. So this kind of actually looked like our x squared example. And then again, let me bring it back to 5, right? So this is the one that we did. The approximation's okay. It does a decent job of approximating the area under the curve. But my goodness, look how nice that is, right? If we had 94 rectangles, this would do a very good job of approximating the area under the curve. Again, not exactly, but very, very close. Okay, so now you can see kind of how we will be using these rectangles in order to get our final answer, eventually. Okay, let's get back to here. I have one more example for you before we quit for now. Example 310. Consider the function, and notice I did not give you an equation for this function, g of t, right? All I did was give you the graph, and I would like you to, again, you really need this conceptual idea in this case in order to approximate, right, the area under the curve. Oops, I didn't want that. Blue, there we go. The area under the curve on the interval from 1 to 4 of this function, right? So here's from 1 to 4. So that's our interval. We would like to use n equals 6. So I'd like to break this up into 6 equal pieces. So again, my a value is 1. My b value is 4. So my delta x value, the width of each one of these pieces, is going to be 4 minus 1 over n. So that's going to be 3/6 or 1/2. And so if you break this up into little pieces of a half, 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 right? You can see that hopefully, if I did things right, there should be 6 of them. 1, 2, 3, 4, 5, 6. Each one of these rectangles has a width of 0.5. That's our delta x value. And now the only thing left is to get the heights of these rectangles, and then I'll be able to get the areas. And so this is where we really need to approximate, because again, I don't have an equation. I didn't give you an equation, right? And so we need to approximate this. All right, and we're using left Riemann sums. So, okay, on this first interval, let's take a look here. We have a choice between the left endpoint and the right endpoint. And again, we're always going to be choosing the left. So I'm going to go ahead and choose the left endpoint right here. So notice how this forms a nice rectangle. Oops, that's a little bit taller than I imagined it would be. So it forms this rectangle right here. And again, I'm choosing the left-hand point because it says it's a left Riemann sum. So okay, if I was going to, again, let me kind of approximate this as we go. So the left-hand sum, or the left Riemann sum, it has width of 0.5, and it has a height of pretty close to 3, right? So I'd say the height of this rectangle is 3. Plus, okay, let's look at the next one, right? So the next one, next subinterval, again, I have kind of 2 choices, here and here. And again, I'm always going to choose the left one, right? And so if I choose the left one, I'm going to have a height here. And so I get the following rectangle. Surprised me again. Here we go. And this rectangle has, again, width of 0.5, and its height, I would say, is pretty close to 2.5, maybe a little larger than that. I'm going to use 2.5. Okay, let's go on to the next rectangle. The next rectangle, this next interval right here, again, I'm going to use the left endpoint. It's a left-hand sum, so I'm always choosing the left between the two. Okay, and so this one has a height of 2. So a width of 0.5, a height of 2. Okay, next one up. Again, I'm going to choose the left endpoint. Actually, it looks like the left and the right endpoints are the same in this case. So the same height no matter what. Okay, and that height is going to be around, I'm going to say 1.5. Again, this is an approximation. So its width, 0.5, times its height, 1.5. So that's the area of that rectangle. All right, next rectangle. Have a choice here, and I'm always going to choose the left one. So there. And so this rectangle is going to be a little bit shorter there. And so this one I would say, again, the width, let me go ahead and add a new line here. The width, 0.5 times the height. I'd say the height is again going to be right around 1.5. And then the final subinterval, the final rectangle, I have a choice between the left and the right, and again I'm always going to choose the left. And so this rectangle is going to be this big. Okay, and again its width is 0.5 and its height is going to be, I would say, around I'll do 2.3. Okay. All right, and again you want to show your work, just in case if your estimations are a little bit different than mine. And let's go ahead and plug this into our calculator. Notice again, every one of these has a 0.5. So actually, before I plug this into my calculator, let me show you a shortcut, right? So let me highlight this to bring out every single one of these has a width of 0.5. Oops, I guess I wrote 0.2 here. I meant 0.5. Catching mistakes, that's good. 0.5, 0.5, 0.5, 0.5. And so if I was to factor all of these 0.5s out, I would just have 3 in the first term, plus 2.5 in the second term, plus 2 in the third term, plus 1.5 in the fourth, plus another 1.5 in the fifth, and then plus 2.3 in the last one. And the claim is that this is just a little bit faster to plug into our calculators. So I'm going to do, again, 0.5 times parentheses 3 plus 2.5 plus 2 plus 1.5 plus 1.5 plus 2.3, close parentheses. And again, a lot of this we could actually do in our head, right? Like the 1.5 plus 1.5 would be 3, 5, 8, 10.5, 12.8, right? Yeah, we could do this in our head, but why risk it? We'll use a calculator. Chop that in half, of course we get 6.4. So the area under this curve is very, very close. Well, I mean, pretty close anyway, to 6.4. You can see over here, these were kind of overestimates, right? The rectangles were too big. Over here, the rectangles were kind of too small, and we hope that it kind of evens out and that this is a decent approximation, 6.4. All right, that is where we're going to end for this video. A little bit of a long one. Sorry about that. I'll give you guys a break, and I'll see you in class.